Hello everyone, welcome back to this lecture, which happens to be the continuation of lecture number 13. And exactly in the previous lecture, namely the lecture number 13, we have seen how to calculate the work done on a unit charge if you are going to move it from a place A to another point B. So as you can see in the board, we can directly see that exactly I am keeping the same board that we have done in the last class. And here you can see that the calculation that we have done is the equation number 3. And let us continue this one. But before that, I would like to make some remarks once again, or to refresh your memory on what we have done exactly in the last class. So our objective, let me write down here in the board. So what exactly we have done in the last class is that we started with this expression F equal to the constant of the proportionality multiplied by the two charges involved in the Coulomb's experiment, and then you have this expression for the R cap. Now, what all we are discussing over last few lectures is that we would like to understand what is this charge doing. When a charge Q1 or another charge Q2 is there, it is doing something. Like something means we are able to feel it in terms of a force. So that is exactly what we try to understand. In order to understand this equation for the Coulomb's force, what we have done in the last class is we have rewritten this particular equation like this by bringing the Q2 down here. So if you do that, we essentially got this 1 divided by 4 pi epsilon 0 into Q1 divided by R square. Then you have an R unit cap. So, and we have explained in the last class that rather than saying a Q2 here, namely in this particular denominator, so let us represent by, or let us denote by a capital charge Q, and we will call this particular charge as a test charge. So if you are going to do like this kind of a notation, then what happens is we will be having a capital F divided by Q, and then that will be given by the right hand side remains the same. So let us write down like 1 divided by 4 pi epsilon 0 into we have a Q1. So now that only one charge is there, so therefore this particular suffix 1 is not required. So I can write down that this is Q divided by script R square into the unit vector R. And then we are going to call this one. So whatever you got here on the left hand side, namely the capital F divided by capital Q, we are going to call this. So we are going to call this and then write by a symbol capital E. So therefore our conclusion finally what happened is that this expression is rewritten as the electric field is given by, it is not that electric field is something which is already defined. As you see that it is basically coming from the Coulomb's law, and therefore we are going to give the name electric field for the quantity F divided by Q that is there here. You can always follow the green color cursor when I am explaining, and therefore F divided by Q, if you are going to represent it by the capital E, then I will be having the final expression 1 divided by 4 pi epsilon 0 into Q divided by R square R cap. And this expression is almost final, but let us write down in a more explicit manner. So what is explicit here is that the electric field is a function of the distance here. So that is what we mean to say. The electric field is a function of the distance, and that is what we write E of R here, and that is equal to 1 over 4 pi epsilon 0 into Q divided by R square. Then you have an R unit vector. So the only additional thing that we have made it explicit, it is not additional. We have made certain things clear by writing this script R vector inside the bracket. And you know what is the meaning of that. When you write in f of x, suppose if you are going to write that f of x equal to, let us say 1 plus x square, the meaning implied by f of x is that f is a function and it is a function of x alone. That is the meaning. So instead of saying that this is f of x, we can also write like this, f equal to 1 plus x square. So both are same actually. Whether you write f equal to 1 plus x square or f of x equal to 1 plus x square, these two things are same. But however, the first one, namely the f of x, gives you an additional clarity. What is the additional clarity is, the function is going to be a function of x alone. There won't be any mixture of additional variables such as y, z, etc. That is the meaning. So additional clarity comes when you write the independent variable in the bracket. So that's what we have written, that we have written for clarity the independent variable, namely the one which is written inside the bracket is the independent variable. And so let me write down that. So this is the independent variable. Independent variable means you can control, isn't it? So when you have two charges, you can separate and keep over whatever distance you like. First of all, you fix it. Afterwards, you can measure the force on it. So that is the idea. The independent variable means you can control it. And what are you going to measure? The electric field is the one which you are going to measure. So that is written in the outside. So this is clear. So let me erase this one now. So this is what we have done in the last class, that once you start with this, let me write down that this is equation number 1. So once we have the Coulomb's equation, namely this equation number 1, we have established the equation number 2, which is the definition for the electric field. So this happens to be the definition of, or we propose that let this equation be the definition for the electric field. And we can understand electric field from this equation. So here is the understanding. So electric field means it is the force per unit charge that is there here. So once you have this concept now, that means once you got the additional concept of the electric field, the next thing that we moved is the understanding of the same electrostatics in terms of the energy. And in order to get the energy, we have calculated something called f dot dl based on our knowledge in the mechanics. So that is what we have done in the last class, and we have done the calculation. So based on the idea of the f dot dl, and from here we have calculated the work done on a charge capital Q to move from a point x is equal to A to x is equal to B in presence of a charge small q. So this is what we have done in the last class, and then we got the result. So let me write down the result. The result that we got is that the W, if you are going to represent the work done on the system, that is equal to small q into capital Q divided by 4 pi epsilon 0 into 1 divided by B minus 1 divided by A. So this is the equation that we are going to use now, and then discuss more about this particular equation. And in order to refresh your memory, you should also remember how the diagram looks like. So we started with this particular point as x equal to 0, and we have some other point as x is equal to A here, and this could be a point x is equal to B. So these are the positions that we have used in the last class, and at the point x equal to 0, we are going to keep a charge small q, and at the particular point x is equal to B, you are going to keep the charge capital Q. And remember, the capital Q was earlier at x equal to A, and then you pushed it and then brought it to the point B. So A and B are 2 points along the line. So this is what exactly we have done in the last class, and we want to understand this equation a little better by doing the following. So consider what happens if you are going to consider the point A approaching infinity. So this is what we want to understand. So we want to understand the equation that is written here. Which equation? This W equal to QQ divided by 4 pi epsilon 0. No, that equation we want to understand better. To do that, we are going to consider a situation where A tends to infinity. What do you mean by A tends to infinity? you go to the diagram here. So this is the diagram. This is your x equal to a. So this particular point x equal to a, so you take it very far away. So consider a situation that a is far away, which is represented by infinity. So remember one thing, that infinity is not a number. Okay, infinity is not a number. Infinity is a large number which cannot be written down. You can't write down a specific number and say that that is infinity, isn't it? So that point should be clear to you. Suppose if you write down any number, you write any number. Let me write down that you simply write down so many zeros here. How many zeros you are going to put, that is up to you, whatever number you put. And let us say that this particular number which you have written is a big number. If you say that this is infinity, then immediately what happens is, you can't say that this is the largest number. Okay, you cannot say that this is the largest number. The reason is, you can always add further zeros. I am now adding additional zeros. In order to make it something clear, or in order to make it clearly visible, I will put the zeros in the pink color. So now I am going to add 2 more zeros here, or 3 more zeros here. And now I will say that this is a larger number than what you have said earlier. Is this point clear? So from here to here is what you have written originally, from here to here, and you are going to claim that this is the largest number and that is infinity. If you say like that, immediately another person can put additional zeros like this. You can always put an additional zero like this and say that that will be a larger number than what you have said. And even this is not the larger number, because again you can add some more zeros here and say that this number is larger than the previous one. And similarly, the story will continue. So the moment you say that this is the largest number, you can always add additional zeros and then say that this is larger than the previous value. And therefore, if you are going to continue this story, where will you end? There is no end for this, because there is no end to the number of zeros that you are going to add. So therefore, if you ask the question, what is infinity actually? Infinity is the very large number that cannot be written down. Nobody can write down what is the infinity. In fact, this is true in the 10 to the power notation also. So you may think that why do you want to go for several zeros writing like this? Instead of that, we can simply say that 10 to the power of something like 299. You can write like this. But immediately what happens? 299 can be converted to, you say that 10 to the power of 300. Now you say that this is the larger number. So like that, the same story will continue. So it doesn't matter in which style you are going to write down the number. In whatever way that you are going to write down, there is no way you can write down a number and say that that is infinity. It's not at all possible. And therefore, such a number is infinity. So you understand what is the meaning of infinity. It's the largest possible number. And as you try to approach infinity, infinity will go away from you. That is what it means. Suppose assume that there is an infinity in this universe and you want to reach infinity. So you step forward and move towards infinity. Then what will happen is, then infinity will move far away from you such that you will never reach it. You can't reach that particular point. So that particular concept should be clear, and therefore we can't write a equal to infinity here. So why I am making this explanation here is, you can ask the question, why don't you say that a equal to infinity? Why don't you write a equal to infinity? You have written a tends to infinity. So there is a arrow here. Okay, why can't you put a equal to here? The reason is that this is what is not possible. Okay, because equal to cannot be written. Equal to can be written only if you have a fixed number and say that a will take that value. Infinity itself is not a single number. You can't represent it. And therefore, you can only tell that a approaches infinity. Approaches infinity means it keeps on moving as much as it can. That's all about it. So as much as it can means whatever possible by that particular system to the best possible situation, to that extent it moves. That's what it means. So basically it is like saying that you just move away from a particular object, then you simply move away from whatever you can. That's all. So there is nothing like you have a fixed value. Try to be far away in such a way that the disturbance doesn't affect you. So as long as a certain thing doesn't affect you, to that distance you go far away and then stay there. So you stay there because that there is no effect of certain thing on you. So what is that certain thing that we are talking about is this Q. So come back to this diagram. So I am talking about some effect here. The small charge Q is going to produce an electric field surrounding its region. Now, how do you know that it will produce an electric field? That is what is the previous equation. It is there here. So just now we have written here this equation number 2. This equation tells you that whenever you have a charge small q represented by a small q, then this will produce an electric field capital E, which is a function of the distance r. So whatever be the distance r, there will be an electric field present. And in case if you want to know how much electric field is there, then you can calculate using this equation. If you don't want to calculate, you can measure. So you can do any one of them. That is the meaning of this particular equation. Our meaning says that the moment you have a charge q, then in the surrounding region, so surrounding region is what is this r. R means any distance away from this particular charge, then it will produce an electric field. That is the meaning of this equation. And therefore, keeping this meaning, now we are standing here that this particular charge small q at x equal to 0 will produce an electric field in the surrounding region. And what do you mean by the surrounding region is in all regions away from x equal to 0. So whatever be the radial distance. Now, when you are discussing this particular point, you should refresh your memory on what we have discussed in a few of the previous classes. We have seen when the Coulomb's law is not valid, when the Coulomb's law is valid. So at that time I told you that when two of the charges are coming closer than 10 to the power of minus 16 meter, for example, then the Coulomb's law breaks. You can't use it. That means any distance less than 10 to the power of minus 16 meter. That's a very small distance. You are going to the subnuclear level. So that is the place where it breaks. Coming to the larger side, we have already seen that even though you keep on moving away from the charge by as long as 10 to the power of 8 meters. Okay, 10 to the power of 8 meter means what? 10 to the power of 8 meter means 10 to the power of 5 kilometers. Okay, so until that distance, you can feel the electric field. So after that, what happens means after that it is approaching 0. So you let me again write down that there is a 1 by r square term is there, right? So this 1 by r square term will make it to 0. So this will approach 0 if r is very large. If r is like 10 power 8. So I am talking about 10 to the power of 8 meter. So if you are going to substitute r as 10 to the power 8 meter, then r square will become 10 to the power 16. Then 1 divided by r square will become 10 to the power minus 16. So your electric field will be of that magnitude, 10 to the power of minus 16, and that becomes too small that you cannot detect. It may be there, but it is too small that your equipments cannot detect. Your equipment will always show 0 there. So which means that the Coulomb's law is valid for all these faraway places, and therefore this small q that you have that is present here will produce an electric field in all the surrounding regions to the farthest distance, such as 10 to the power of 8 meter. So if you cross 10 to the power 8 meter and go away from this, then the electric field will not be felt because it will be there, but it is too feeble almost. So it is 0 only. Any number which is less than 10 to the power of minus 16 that you are unable to detect in your equipment, and therefore that limit is something you consider for practical purposes. You say that electric field goes to 0. So you are going to run away from the charge by such a large distance, 10 to the power of 8 meter. If you are going to do that, then practically we can say that we are approaching, or we are making a meaningful sense of A approaching infinity. See, all this explanation I am making in order to make you comfortable by the statement that if A tends to infinity. I have written here A tends to infinity. So infinity is anyway not possible. It's not at all a number. It is not at all a number that can be written down. If it is the case, then how can you achieve A tending to infinity in practice? In practice means when you are performing an experiment in the laboratory. So that is the meaning. The answer comes here. So suppose if you run away from the charge by a distance of the order of 10 to the power of 8 meter, if you go out of charge by that distance, then practically it is equivalent to A tends to infinity. even though it is not infinity, because its effect is not felt. You don't feel as if there is a charge is there. So you have gone too far away so that it appears that the charge itself is not at all present. So such a condition is what we say A approaching infinity is a meaningful one. So once this is clear to you, now then we can go back to the equation and then substitute. So before that, let me erase this. Okay, once you are clear about A tends to infinity, now we will go back to the original diagram that you have here. This x is equal to A, this particular point, this is what we are talking about, and this point has to go to infinity, which means you simply go to a farthest place possible. And then once you are there, and from there you have to come. You see what is this particular thing? You are going to come from here. So this is, let me draw here. This is the point A and this is the point B. Same thing I am drawing. This is the point B I am drawing. And what is actually that you have done in the experiment is, from the point A to the point B, you are going to travel. So you come like this. Travel means you are taking the capital Q charge and then moving in this direction. You are pushing it. And you are pushing, and then you are keeping it at the point Q that is written here. So you are pushing the charge and then keeping it at the point capital, at the point x equal to B. So that particular scenario you should remember when I am explaining. So basically now we will come back to this equation, that if you are saying that A is tending to infinity, the meaning is you are essentially taking the charge capital Q to a farthest possible distance, and then pushing it from there and then come to the point x equal to B. That is the meaning. So if that happens, then we can write down that W equal to Q into Q divided by 4 pi epsilon 0 into, you get 1 divided by B minus 1 divided by infinity. And 1 by infinity you can simplify. So that gives you Q divided by 4 pi epsilon 0 into 1 divided by B. So this is the expression for the W. Now we want to understand this equation. Okay, there is some equation, but however, only when you understand the equation, you will also understand actually the electrostatics, what is happening, what is the effect of the charge, and how to understand more about the electrostatics. That will be clear only when we try to understand this final equation that appears like this. So that's all. Our conclusion is this, that we have an expression that is looking like this. But how to understand this equation? Now, in order to do that, what you do is, you bring this capital Q to the denominator. Because here you have a W. W is here, Q is in the numerator. Bring it down here so that it becomes per charge, per Q. So in the last class I explained per unit charge, what is the advantage I explained. So that is what we are doing. It is the work done per unit charge will be given by 1 divided by 4 pi epsilon 0 into Q divided by B. And that's all. So this equation is reasonably good, and this is now comfortable that you can understand this. Now what we will do is, we will call this quantity. So let me put this. So this one we can understand as work done on Q per unit charge. So it is a work done on the Q, that is clear, because the last class also we have done that. But however, we are now saying that it is per unit charge because you have divided by that amount of the Q. Okay, so once if this is clear, then what is an advantage is, we can give a different name for this because it is going to take a different physical dimension. You should understand one thing. Whenever you do this kind of division, what happens is, the dimension is now different. If you are talking about only W, see here, this particular W, then the dimensions are joules because it is energy. Now you have divided by capital Q. So therefore what happens, this is joule and this is now coulomb. So joule divided by coulomb means it's a different physical dimension. And therefore, because it is a different physical quantity, we can therefore give another name for this. So the another name that is given for this is the potential. We are going to give a name potential for this W divided by Q. Same W divided by Q. We are going to give the name. How we are giving the name is based on the same thing. Whatever you see here, just to go back. So you ask the question why you see this. We are going to call this the electric field. So why do you want to give the name? Means that is the name. You have to give some name. That's all, right? You cannot keep the same name. F means force. Now coming back to this particular situation, you have F by Q. F by Q cannot be Newton, because numerator is Newton and denominator is Coulomb. So it is Newton divided by Coulomb. You can simplify it. It has to be a different physical quantity. And we are going to give a name for that. And the name that is given is electric field. Similarly, instead of doing the F divided by Q, now we are doing W divided by Q. So that's exactly what is happening. So you come here and now here you have a W divided by Q, and now the physical dimension has changed, and therefore we have to give a new name. The name that is given to this object is electric potential. Because this is electrostatic, it is electric potential. And in order to avoid confusion, if you want to write electric potential, you better write. Because as we go along, we are going to read something called magnetic potential. So that is a different thing. So magnetic potential is different, electric potential is different. So to make it clear, you write down that this is the electric potential. So this is the electric potential that is due to the small q at a distance b. That is given by the same expression you write down. That's what you have got it now. So that is 1 divided by 4 pi epsilon 0 into q divided by b. And this is what is the important understanding that you are going to get. Okay, let it be equation number 3, for example. So now when you are making this particular statement in English, there is something interesting that you have to note down. What is the interesting thing is, when you are writing using the symbol capital Q, you see this on Q is there, on capital Q. The word capital Q is present. When you are changing the name W by Q as the potential, you are changing the name as electric potential. The capital Q has disappeared. That is what you have to see this. The same equation did not change. But however, when you are writing this thing in order to explain or in order to understand, we write like this: electric potential due to small q we are writing, not capital Q. So our understanding is now comfortable in such a way that the capital Q has totally disappeared. So this is our interesting point. So since we are going to consider this W divided by Q, and that is what is the electric potential, we are going to define. So let me write down here. So I'm writing like this, but remember, electric potential is now expanded, because if you simply tell electric potential, it's not clear. You have to give further explanation. So electric potential is due to what? From where it came? So due to small q, it came from small q, not from capital Q. That is important. Electric potential came from the small q, and it is present everywhere in the surrounding region. And if it is so, then at a distance of b from the charge, how much is the electric potential? And that is given by this expression that you have. So this is the meaning implied by whatever calculation that you have done now by substituting infinity here. So again, I'll tell you. So you see why infinity we have substituted. By substituting in infinity here, now we are able to understand another physical quantity which is useful to understand the effect of the charge. Once again, I'll tell you that our objective is we are studying electromagnetism or electrostatics. For the time being, we are studying electrostatics. We don't consider the charges in motion right now. Under that, we want to understand what is the charge doing. That is the question. The answer is charge is creating a force. That is the first understanding. The second understanding is the charge is creating an electric field in the surrounding region. Second understanding. Third understanding is the charge is producing or the charge is creating an electric potential in its surrounding region. Everything is same. Whether you write 1, 2, 3, all the three are same, but it will be easier for we to understand any one of them. One of them would be more comfortable than other. That is exactly what we are doing. So we have seen that this is an equation number 3. The first one being the force understanding. The second one is understanding in terms of electric field. And the current one, namely equation number 3, is the understanding in terms of electric potential. So this is the important concept. It is not that you have these formulas and then we write down and memorize. So there is nothing like that. It is only one experimental discovery was there. That was the one done by the Coulomb. And in order to understand that particular force equation given by the Coulomb, we write them in a different mathematical possible ways and then try to understand the same equation as much as possible. That is exactly what we are doing. Now, in order to understand this further, let us rewrite this equation slightly better form. We are going to rewrite this equation, the same equation, in a different way, slightly. So what is the change that we are going to do is, instead of writing in English sentence electric potential, let us give the symbol for electric potential, which is capital V. Because W is the work done, capital E electric field, capital F is the force. So like that electric potential, we will give the symbol capital V. Immediately the question comes, is it a vector quantity or a scalar quantity? And the answer is there in previous expression. So you see that the electric potential is defined by, here you have W divided by Q. What is W? Work done. Work done means scalar. And in the denominator you have charge. Charge is also scalar. Therefore scalar by scalar is a scalar. Therefore the electric potential is a scalar quantity. So that much is clear. First point is clear. The second point is, electric potential is calculated at a particular distance B, and that B appears here. Okay, so if you are going to substitute B as 3 meter, then you have to substitute a 3 meter here. That is the meaning. If you are going to 27 meter, then this has to become 27 meter. So it's clear that electric potential is going to be a function of this particular distance. Therefore, similar to your mathematical way of writing f of x is a function of x, now we say that the electric potential is also a function of. It's a function of what? It's a function of the distance. So let us write down that the distance we are going to have a standard symbol r. Because we are in electrostatics already, in the very beginning itself, I have explained that we will be preferring the symbol script r for the distance, where we have some preference when compared to other ways of writing the r. So that we have explained in some of the previous lectures. So therefore the distance is now written as r. It's a function of distance. So that is equal to, so that is clear. So by writing this, what is an advantage? The English sentence is now removed. But however, you should remember that the meaning of V of r should be this. So if the meaning is not there and if you are only writing the equation, then again that is also useless. So we are now writing as V of r for all the meaning here, namely V of r represents the electric potential due to a small charge q at a distance b. That is the meaning. Now we are going to write r in terms of b. Okay, there is a b here. This b we are going to give the renaming. We are going to change the name as r here, and therefore that will be equal to, you write down whatever is there here on the right hand side, that is 1 divided by 4 pi epsilon 0 into q divided by, so this is b means this is also b. So if this is r means that also will be r. So I will write down that this is r. So this is what you have, and as you can see that this is a scalar quantity. Therefore there is no need to worry about any unit vectors coming into picture. And that's the equation. And let us make one more small modification so that things will be much better. This is fine, there is nothing wrong, this is fine. But we will write down this same equation in a very slightly modified way so that this equation is somewhat clearer than the previous one. So what is the changes that I am making is, V is a scalar quantity, capital V is a scalar quantity I have written. Now you ask the question, this script r that is written here, is it a scalar or vector? You get a doubt, but generally r is a vector quantity only. So if r is a vector quantity, then why the entire thing is scalar? That doubt will come. Then you have to go back and see this how this equation was derived. So when you are making the derivation of this equation, this capital W, work done was there. Work done is obtained by F dot dl. You took a dot product. So because you have taken a dot product, the vector has disappeared. And therefore, then as you can see, what is this B that is written here must be the distance in scalar. It is not, it is a distance that is clear, but it is not a vector. Because dot product is there, so the unit vector has disappeared. And what is left out is only magnitude. So that is the point that we want to make it clear by rewriting this expression as it is a magnitude of a vector. So like I'll write down that this is the magnitude of the vector and then close the bracket here. So V of, you write magnitude of a vector, which means that this R is a scalar. You are emphasizing that R is a scalar. We are not interested in the direction. That is the meaning. That is equal to 1 divided by 4 pi epsilon 0 into, once again, this is also Q divided by modulus of R vector. So this gives you a clear indication that the R that is used in the previous equation is a scalar only. There is no confusion. And in addition to that, the quantity appearing inside the bracket is also a scalar quantity. So this clarity will be there if you explicitly write down so that there will be no further doubts arising. So we will now call this particular equation as, anyway, equation number 4 is not much different. Anyway, 4 and 3 are very similar, small symbols only is changed. And we can now use this particular equation as the definition for the electric potential. And whenever you want to get the meaning of equation number 4, you should always go back here. So if you go back here, then you will be getting the meaning. Because you can always memorize some equation. Then after that, if you ask the question, what is that equation and can you explain what is the meaning of the equation, means you should know. Okay, so that is why we are not going to, first of all, we are not going to write down any equation and then memorize like that. So since we are doing in a particular systematic way, then the meaning comes first. You already got the meaning and then we are writing down the equation as equation number 4. So this is our conclusion is that we are getting a better way of understanding the effect of the charge. So it is clear that the charge is the source. So let us write down this particular one. Q is the charge that we have, and we are going to give the name as source here. So this is the standard terminology in electromagnetism. So there will be a source and there will be a field. So because of the source, what happened, or because of the charge, what happened means the charge is generating the electric field in its surrounding, or you can say that the charge is generating an electric potential in its surrounding. So you can say that either potential is there or electric field is there, or it can exert a force in the surrounding region. All the three are identically same, but each one is in a different style. The last one represent only in terms of magnitude without referring to the direction, whereas the electric field and the force will be with the direction. So you can always understand the effects either with direction or without direction. If the direction is attached, then electric field or the force. If you want to understand things without direction, then electric potential is a good idea to understand. So therefore the Q is what is written as the charge, and the charge is what is known as the source in electrostatics. So this is the source in, we say that it is electromagnetism. Now because of this source, so that's what let me write down here. So this is what you have, and therefore this will produce. So the effect will be, effect is produced by the source. So the effect is produced by the source, and the effect can be anything. So let me write down therefore that the effect will be is to produce an electric field. So this is our final understanding that we need not write all the three of them. You should remember one thing, that we have now three of them. One is the force is generated in the surrounding region when another charge comes, or electric field is present, or there is an electric potential. Should we write all the three here? Is not all the three is not necessary, because any one is enough. Anyway, other two are derivable. As you can easily see that if you started with only one of them and then you start to derive the other things. Therefore, you can consider only one effect, and whenever you want to understand in terms of force, or if you want to understand in terms of the electric potential, you can always jump from one equation to the other. But therefore, there is no need to specify three effects. You should not say that there are three effects are present. Like that, it is not required. You only say that one effect is that it produces electric field. You can only say that it is equivalent to saying that there exists an electric potential. That is okay. It is equivalent to saying, that is fine. You should not say that this is second effect is there, that electric potential is there, and third effect is it will generate a force. Like that you need not say, because each one of them is one way of understanding the same thing. So we have a cause and effect relationship. Okay. So this relationship should be clear. There is a cause and then there is an effect here. So the cause effect relationship is that cause is the charge small q that we have. Capital Q generally we reserve for the test charge. That is why I use the word small q. So cause is the presence of the charge small q, and then the effect is that it will produce electric field in its surrounding region. In its surrounding region, it will produce an electric field. That's what is the meaning. So here, this is enough. Once this is clear, the rest of the thing can be done by further calculation. So this is our understanding in electrostatics, that as long as the charges are static without, that means there is no motion involved in the system, then the primary effect or the main effect that the charge is going to produce is to produce an electric field in its surrounding region. Electric field is generally preferred when compared to the electric potential, because electric field contains both direction and magnitude. You have magnitude also, you have direction also. But if you are going to discuss purely on the electric voltage or electric potential that you have written here, then you are actually, separating out the direction and throwing it out. The information about the direction is lost in the equation number 4. You see here in the equation number 4, you don't have any reference to the direction. So therefore, there will be some loss of information when you are discussing, when you say equation number 4. So whenever we want, we can use it. That's the meaning. But full information will be available when we are considering the electric field E. Therefore, it is preferred to say that the cause of the charge is to produce an electric field. So this is the main conclusion. Okay, so let us further understand the same equation once again that we have written down here. So let us now go back to this particular stage, and we have this equation W equal to QQ divided by this. Okay, so I am now referring to this equation once again, because this is the equation that we discussed at the end of the last class, and today we are starting with this equation. So again, we are going to go back to this equation and ask the question, and how do you find out the dimensions of this particular quantity? Because left hand side, you remember, left hand side we have calculated using the expression F dot dl based on the idea on mechanics. Okay, you have F being the Newton and the distance being meter. Simply it is Newton meter you have written, and then you got this W. But on the right hand side, you have a different set of units, electrostatic units. So if I am going to substitute that, then how this will look like? So that can be done here itself. Maybe I will try to write this in a different place. I'll go to the different place in the board, and then let us see what is the expression. Okay, so let me write down the equation once again. We have W is equal to small q capital Q divided by 4 pi epsilon 0 into 1 divided by B minus 1 divided by A. So we want to understand the dimensions, or what are the units for that. Okay, so that will be easier. Let us see that this will be in Coulomb, and capital Q is also Coulomb, divided by 4 and pi doesn't have any units, and epsilon 0 has the dimensions of farad per meter. So this is farad per meter is for epsilon 0 into 1 divided by b. B is a distance, therefore I will write it down as meter. Then minus 1 by a will not affect, because 1 by b minus 1 by a will have 1 by meter. And that's all. So you now simplify this. So this becomes right Coulomb square divided by, so this meter inverse meter cancels. I'll get Coulomb square per farad. So this is the one that you have to simplify. Coulomb square per farad. So it's not difficult. Let me show here. If you take the capacitor equation that you know, Q equal to CV for a capacitor. So what is the meaning? The meaning is that this is a Coulomb that you have should be equal to capacitance is a farad multiplied by the V is in volt. So we can write like this. So based on that, we can write down what is F. So the farad can be written as Coulomb per volt. So use this idea and then simplify this. So that gives you, this is a Coulomb square divided by, and here you have F. F means Coulomb. So here you can write down Coulomb per volt. So I'll write down per volt means volt to the power minus 1 I'll write. Okay. So if you simplify this, we will be getting, so that is a Coulomb. Then you will be getting multiplied by voltage, VOLT. Okay. So this has to be simplified. So now in order to simplify, you use the definition for the Coulomb, and the definition for the Coulomb is ampere multiplied by second. That is the definition for the Coulomb, then multiplied by the volt. So that gives you have ampere. Let me write A for ampere. I'll write V for volt. So that I will write here V for volt, and then seconds I will write S. And that's all. So you have A into V into S. And now you have to simplify this A into V into S. And what is A? A is the current. Let me write down that A is the current I. V is the voltage. So that voltage I will write here. Okay, so this I am writing separately. Okay, so to put a line here. So you have AV. AV is nothing but current times voltage. And you know that current times voltage will give you the power. That is known to you. Current multiplied by voltage is power. And what is power? Power is actually joules multiplied by second. Is it clear? Joule per second is the power. So this V into I, that is your A into V. A for ampere. A is ampere, here I is ampere. I is current. Okay. So this is the ampere that I am writing. And therefore this product will give you joules. So on the left side, what you have, on the left side you have a W, and that is actually nothing but we started our calculation using F dot dl. So our conclusion is that the equation for the W is having the dimensions of joules. So I'll go back here. Yeah, here, this one. So this will be having the dimensions of joules. And that's all. So it is only a simple thing, but I want to make it clear that the equation that we obtained by doing some integration, you got this equation by doing some integration, right? And so we are now happy that the idea of F dot dl taken from the mechanics, and even though we are doing with the electrostatics, we ultimately get the object joules. So therefore, you can always say that W is the work done, and therefore you can always say that that quantity represents the energy. Because it is joules, it also represents the energy of the system. So this is first point. The second point is, you can also do a similar analysis for the second equation. So where is the second equation in our board? So let me go down to the previous board. So after that we have done some calculation, right? So where is that calculation? Here it is. So this is the W is over. So now I'll put a tick here. So now you know that this is in the joules now. So afterwards we have done one more calculation, W divided by Q. So if you do W divided by Q, what will happen? Okay, so that here itself we can write down. So this gives you that W divided by Q, if you have corresponding to this equation, then that gives you joules. divided by Coulomb. So Q means Coulomb, right? So I'll write down that. So that gives you, this can be easily cancelled and then show that this comes to the volts. Okay, so this cancelling and bringing to volt is only a very simple thing, and you already know because I have written here. So where I have written this one. So this is the place where voltage is coming. So this is what you have, this again you have to manage with this equation and then bring it down there. And because of this reason, once again let us make the conclusion on this particular expression. So we are making a conclusion that this quantity, since we have a W, here it is there, since we have made the W divided by Q and having the voltage as the units, we now write that this is volts. And why do you want to make this kind of small understanding in terms of the units is that we can now understand what do you mean by the volt then. So we can write like this. Therefore, volts or whatever you call that, potentials, or let us say electric potential, is nothing but work per unit charge. So this understanding will come only when you perform this kind of a small calculation. So what is the meaning of an electric potential, and that is measured in volt? Why we are giving the volt as the units for electric potential? If you ask that question, the answer is quite trivial, that you are going to substitute the suitable dimensions for, here it is, suitable dimensions for W and charge, and it naturally cancels out and comes to be as volt. That's why we are using the volts as the measurement unit. And then if you want to understand what is that actually volt is, essentially the W by Q, which means that the work done to move a charge. Now once again we'll understand this. It is a work done to move a charge. Which charge you are moving? Capital Q. Capital Q is the charge that you are moving. Okay, you are moving from where to where? From where to where you have to tell. Now, in order to make things clear, again you go back to this equation. From where to where is here. So this is your from. From where to where means this is the from. That is, this particular charge capital Q should be far away, something like 10 to the power 8 kilometer away from you. From there, it has to come. Where it has to come? To the point B. So I'll write down that this is to the point B. So your from and to answer is here. Okay. So and therefore, when you understand whatever we are doing here, then everything will be clear. And when you ask the question, what is electric potential? So what is electric potential means? It is the work done on a charge capital Q in order to move it from infinity to the point B in presence of the small q, in presence of the charge small q. So the in presence of the charge small q is important, because if the small q itself is not there, then there is no calculation and simply the work done is zero. So that point is important. In presence of the small charge q, all these things are happening. Okay, so let us have this kind of a conclusion now, that we have an expression for the capital V, and then we have the expression for the electric field. And I would like to emphasize that, this, that you have made a kind of modulus of the R vector here. First few times it may be difficult that writing inside bracket and then modulus, but once you got practiced, you always write like this. F of x is very convenient for you. Now you don't write f of modulus of x vector, but like this you are not writing generally. But now what happens is, x being the distance, it naturally happens to be a vector quantity. Therefore, this gives you a clear idea that in the electrostatic situation we are using only the magnitude. So that is why this particular expression is useful.